continuation of the recap of determinants. The video's being a little weird and the computer's being weird, so it's hard to check the video. So let me just go back a little bit to make sure I didn't, that it overlaps. So if you need to fast forward through something, it's fine. Not that I never know. So anyway, so we want to think about there's really three cases, and I want to contrast them. That's one way to say it. I want to compare if I have u and then I take v and I add a multiple of u to that. And I think this came through in the previous video, but we'll see. It's worth recapping. Here's u, here's v. And then this is very special what I'm doing here, is I'm sliding v parallel to u. So instead of having this parallelogram, I slide v, but I don't slide it in any random direction. I slide it parallel to u. And so the base is not changed of the parallel, if I think of u as the base, and the height has not changed either. And the orientation has not changed. And so a row replacement operation does not change the determinant. A row replacement operation, that kind of row operation, that most interesting one, in fact, the most used one, does not change the determinant of a matrix. At least for 2 by 2. We haven't thought about higher examples, but you can probably guess what's going to happen. At least for our geometric intuition, it seems to be good for 2 by 2. Now, what about if you have det of uv, det of, actually, let's say v plus w. How does that relate to det of u, v, and uw? Now, it's a little bit of a different picture. I'm not adding a multiple of this top row to the middle bottom row. I'm adding some other vector. Well, we have looked at the case where v and w are parallel. So here's u, here's v, and then here's w going off. And it was pretty clear that these areas just added. If v and w were really parallel, not anti-parallel, not opposite directions, but we discovered that if you're careful enough with the signs, it lets areas cancel each other out with negatives. It actually looks like it works even if they're anti-parallel, if they're generally in an opposite direction. So if v and w are parallel, and that includes anti-parallel, right, as a negative parallel. Okay. So this is one case, this is the second case. They're really rather different. Because here I was adding in a very special vector that was geometrically interesting coming from here, that it was a multiple of u. Here I'm adding in something that's very special, but for a completely different reason. It's basically a multiple of v. And I get very different rules. Here, the determinant didn't change. I didn't have this is equal to a sum of two factors. A sum of two terms, rather. Here I do have a sum. So you want to keep those straight. And then the third one is, what if v and w are not parallel? That's a little more complicated. We're going to get to that case, but I don't want to assume anything about it yet. We don't really know if this very nice rule would work for that case. Another thing to note is, if you give me this and this, you might be tempted, oh, the determinant of this plus the determinant of this is a determinant where I add the bottom rows and I add the top rows. But notice it's not a 2u. It just would be wrong. And also, if this is like u1 and u2, could I put a u1 plus u2 here? It's just not true. It's not true even if u1 and u2 are the same vector. So beware. There is not a real simple rule for just taking two determinants of two basically unrelated matrices and adding those determinants. There isn't a good rule. We won't even discover it. There isn't one. Okay, it's not like we haven't got it yet. There just isn't one. So there's still work to be done on this case. And then even with the cases that we know, it's good to keep them straight. So we can summarize what we know saying that a row multiplication multiplies the determinant by whatever your factor is. So that's like this. And the same would be true if I multiplied the top row. A row exchange, and I summarized this at the top of part 3. Changes the sign because of the signed area issue, and the row replacement operation, even though it's the most interesting of the operations, it's the one that does nothing to the determinant. Now that doesn't mean it's a stupid fact. It's a very, 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 very useful fact. And I meant to say that many variations because it really is that useful. So let's use that. In number 7, we want to find out the determinant of A, B, 0, D. Not a completely special matrix, but not completely general either. Okay. And all right. So if D is equal to 0. Then one of these things is the 0 vector. It's just it's collapse. The 0 vector is definitely gonna give a 0 because one of the sides of the parallelogram is 0 length. Okay. If D is not equal to 0, let's use this. Then det of A, B, 0, D. I can use this non-zero guy as a pivot and kill this guy. And we could go through, it's like multiplying, it's adding minus b over d times the bottom row to the top row. It doesn't even matter what the row operation is. We know that we don't have to really keep track of what it is as long as it's a row replacement operation. And this is a rectangle, and it's AD. Remember, it's not absolute value of AD anymore because it really is assigned area. So that's a little bit of a simple example of the basic idea of how we're going to calculate determinants, is using row operations to get it down to examples that we already know that are really simple. Okay?